Hey everyone! As a hematologist specialist, I spend my days looking at the very building blocks of life, your blood cells. Today I want to take you inside the lab to explore one of the most common medical tests in the world, the complete blood count, or CBC, and really dig into the incredible story of how we count your blood.
Okay, let's just start with this mind-boggling number, 25 trillion. That's more than 3,000 times the number of people on Earth. Now, obviously, we don't count all of them. We start with just a single drop of blood, but even that tiny drop has millions and millions of cells. So how in the world do you count them accurately without losing your mind?
Well, for decades, the lab had two very different answers to that question. On one side, you've got the classic, super meticulous manual method using a microscope, and on the other, the modern revolution of these high-speed automated analyzers. This is basically the story of man versus machine happening right inside your blood sample.
Let's travel back in time for a minute, just to really appreciate the incredible skill and, honestly, the artistry it took to do a manual CBC. For generations, this was the gold standard, and let me tell you, it required a seriously steady hand and a sharp eye.
The whole thing was like a multi-step ritual. First up, a tiny, precise amount of blood gets carefully diluted. Then it's loaded onto this special slide that has a microscopic grid etched right into it. It's called a Neubauer chamber. A lab tech then has to peer through a microscope and painstakingly count the individual cells, one by one, square by square. And after all that, they have to crunch the numbers with formulas to scale that small count up to a final result.
Now, here's the thing. For its time, this method was amazing, but it was just so prone to error. Technicians could easily misidentify cells, maybe mistake a lymphocyte for a monocyte. Even physics worked against them. The larger cells would naturally get pushed to the edges of the slide, totally skewing the count. But maybe the biggest problem of all, you're counting just a few hundred cells to represent millions. That's a huge statistical error. It's kind of like pulling 10 people and then trying to predict a national election. It's just not that precise.
So all these challenges, the slowness, the difficulty, the risk of making a mistake, they were basically crying out for a better way. The stage was set for a massive technological breakthrough that would completely change hematology forever.
And the story of that breakthrough starts back in 1953 with an inventor named Wallace Coulter. He had this radical, almost ridiculously simple idea. But when he took it to his attorneys to try and get a patent, they were just baffled. They famously told him, "You can't patent a hole." Well, turns out he could, and he proved them all wrong.
So here is the genius of what we now call the Coulter principle. It turned cell counting into this elegant electronic process. Imagine a digital turnstile. You take a blood sample, dilute it in a conductive fluid like saline, and then pull it through a teeny tiny hole. Now there's an electric current running across that hole. Because blood cells don't conduct electricity very well, every time a single cell passes through, it breaks the current for a split second, and that creates a pulse. Each pulse is one cell counted. Simple, right? But here's the kicker. The size of that pulse tells you the size of the cell. Absolutely revolutionary.
And this principle just blew the doors wide open for machines that were not just more accurate, but unbelievably fast. Modern analyzers that are built on this idea can count over 10,000 cells every single second. A job that took a human technician minutes of intense focus could now be done literally in the blink of an eye.
But wait, it gets even cooler. Modern analyzers go so far beyond just counting. Let's peek inside and check out the incredible tech, like lasers and advanced software, that let us analyze cells in way more detail. One of the most powerful tools in these machines is called flow cytometry. I know, the name sounds super complex, but the concept is actually brilliant. It's a way to force cells into a perfect single-file line and then shoot them one by one through a laser beam. It's kind of like putting each individual cell under its own microscopic spotlight for a split-second interrogation.
So as a single cell just zips through that laser, detectors are measuring how the light scatters off of it. Light that scatters forward tells us about the cell's size, but the light that bounces off to the side at a 90-degree angle, that tells us about its internal complexity. Things like the granules inside a white blood cell. We're essentially identifying each cell by its unique light signature.
So what does all this laser blasting get us? Well, it lets the machine perform what we call an automated differential, which is just a fancy way of saying it can classify all the different types of white blood cells. A basic analyzer gives you a 3-part differential, but the more advanced ones give you a 5-part or even a 7-part, separating cells into really specific categories and even flagging if it sees immature or abnormal ones. It gives doctors this incredibly detailed snapshot of a patient's immune system.
Okay, but how do you make sure you're only zapping one cell at a time? Well, to do that, analyzers use this really clever trick called hydrodynamic focusing. A sheath of fluid basically wraps around the sample stream, and it gently squeezes the cells into a perfect single-file line right as they get to the laser. This gets rid of what we call coincidence errors, which is what happens when two cells try to sneak through together and get counted as one. So you can see, automation isn't just about being faster or more precise. It's about unlocking powerful new data points that were completely impossible to get with a manual count.
These analyzers automatically calculate all sorts of brand new parameters. Take RDW, for example. That stands for red cell distribution width. Sounds technical, right? But all it tells us is how much variation there is in the size of a patient's red blood cells. And that's a huge clue for diagnosing different types of anemia. The machines also create these visual charts of cell populations called histograms, and they automatically flag any result that's outside the normal range, basically shouting, "Hey, a human needs to look at this."
All right, so after all that, let's put them head to head. In the modern lab, how do these two methods really stack up against each other? What's the final verdict?
I mean, when you lay it all out like this, the advantages of automation are just overwhelming. It's exponentially faster. It's way more precise because it's counting tens of thousands of cells instead of just a few hundred. And most importantly, it removes all those subjective human errors that were just part of the manual process. The machine gives the same standardized result every single time.
But, and this is probably the most important point of this entire conversation, you might be thinking, well, I guess this amazing technology has made the human expert in the lab obsolete. And that could not be further from the truth.
See, despite all this incredible tech, you have to think of automated cell counters as extremely powerful screening tools. Their main job is to quickly and efficiently sort through all the normal samples and clear them, so they can flag anything that looks abnormal or unusual. The final, critical interpretation of an abnormal result, identifying bizarre-looking cells, confirming a leukemia diagnosis, or spotting parasites in the blood, that still requires a well-trained human eye looking at a blood smear under a microscope.
And that leaves us with a really fascinating thought, doesn't it? The machine provides the data. It gives us the speed, the precision, the numbers. But it's the human that provides the wisdom, the context, and the final diagnostic judgment. So in the modern lab, it's not really man versus machine at all. It's man with machine. Technology and tradition working together, giving us the absolute best of both worlds to understand the incredible story being told by our blood.